Thanks for the introduction and everything, of course. So yeah, I think this talk is going to be slightly different from the rest today. Like, it's really just a survey talk into this area. Like, I want to get you guys excited about sum of squares and sum of squares law once again after all these years. So maybe let me just get started. And this is not based on any particular work. But yeah, anyway, here's the roadmap of the talk today. I'm going to tell you a little bit about sum of squares, get you excited. And I want to convince you that it's something that cryptographers should care about as well. I'm going to look at the phenomena of information versus computation gap and get a sample of techniques from linear matrix theory. And I'm going to give a quick survey of what we know so far in sum of squares law bounds and how are they usually done. And finally, I want to wrap up with like what kind of question one might ask from and for sum of squares law bounds. Going further. So let me start by telling you what's SOS. So sum of squares, many of you might already know, this is the hierarchy of semidefinite programming realizations. And it usually just starts by giving a polynomial system in X, and each polynomial is a mononomial polynomial in X. And the question is just whether to decide whether a given polynomial system has solution. And you might ask, okay, why are you looking at polynomials? It turns out that polynomials are pretty versatile and expressive. And they find applications in various areas, computer optimization, crypto, and even optimal control, just to name a few. And here's what we know, like in the early age, we already know that every satisfiable system has an SOS proof. But what matters to us is really that such proof can be found algorithmically. Due to the work of Polino and Lasserre, we know that a degree D sum of squares proof can be found and is all decided in poly nm to the order d time. So this gives us a natural trade-off between running time and the proving power of the realization. And crucial to the polynomial system is the degree of the polynomials that we look at. Like, as you might guess, the higher degree of the polynomial, like the stronger the proof system it would be. And in sum of squares, we usually parameterize things by sum of squares degree. And by the previous result of Polino and Lasserre, we can say that degree D sum of squares runs into the order D. And we usually consider sum of squares as starting from degree 2, and it captures linear programming and spectral methods. And actually for this talk, we can roughly equal sum of squares and spectral methods for reasons to be specified in a bit. And here's the interpolation, like basically constant degree sum of squares give us polynomial time computation, and as we increase the degree, so all the way to n, we can actually get an interpolation all the way to exponential. Okay. And while we're looking at this, it is quite powerful algorithmic paradigm. It captures many best-known algorithms. For example, one of the best-known, well-known example is mascot. We try to find the mascot of a given graph, and it turns out that degree 2 sum of squares, which is essentially Goldman-Williamson SDP, gives us 0.87A approximation for the mascot, and this is even optimal under unit game. And of course, mascot is not the only example. In the worst case problems, we have other examples including sparse mascot and CSP and more. But what's really important to us is that sum of squares is also powerful in the average case setting, which is what cryptographers care about, I presume. It is the best known algorithm so far in tensor sparse PCA and random CSP representation chromatic number certification on this problem. So I hope I convinced you that sum of squares is a reasonable candidate if you are interested in algorithmic results in average case setting. And on the other hand, if you're pessimistic about algorithms, you might want to show law bounds against sum of squares to provide evidence of algorithm of like intractability. I think this concludes the first part of the talk. And now let me tell you about the phenomena of information versus computation gap and how it comes into play with cryptography.
Okay, I guess I don't know much about some squares, but like when you say average case setting, like I heard you say that a couple times, but I didn't see it coming through in the description.
Okay. The average case setting, I'm just talking about a large family of problems.
Oh, okay.
But it's gonna be clear soon. I think this slide is about what we mean by average case problem.
Okay.
And we're going to revisit one of the classical predicate questions. The predicate question asks for a random graph sample from GMP. In fact, we're just going to consider P equal to 1/2. So it's a graph on n vertices, and we sample each possible edge ID with probability 1/2. And after we sample the graph, we are going to put in a clique of size k by randomly sample a subset of vertices of size k and then putting every business edge so that they form a clique in the graph. And the question is to ask when can we find the k clique we just put in. And this has been studied since the 70s. And it also has been applied to give like public key for one-way function. This work by Jules. I think it's one-way function. I think the one-way function is true, but the public equator is like both. I think the candidate was both earlier. And here's what we know about this question, classically. We know that using Moore method, you can show a random graph to have the largest clique concentrating around size 2 log. But the best algorithm we know only works for the planar clique of size bigger than some constant times 2n. And this gives us the information threshold of 2 log n. This is what we know from Moore method. And algorithmically, we know how to find the clique when k is bigger than 0 n. And this is achieved by a special algorithm. And let me tell you about this special algorithm. In fact, I'm going to, instead of considering the search question of finding the actual planar clique, I'm going to consider a slightly weaker question of distinguishing. I'm going to give you a rough sample that is promised to come from either of these two distributions. The first one is the genuine distribution of Gn 1/2, while the second one is Gn 1/2 with a clique hooked in. And the algorithmic task I want to solve is whether you can distinguish where the graph comes from. And here's the claim. The size of the clique in the graph is upper bounded by the special norm of the adjacency matrix. +1, let's ignore the +1. And here we're going to consider the adjacency matrix in the ±1 basis. And here's the usual definition of special norm. And now let me show you this tool. We're going to just consider any clique as graph, and then we're going to consider the indicator vector for this set S, and put 1 over root S for any vertex in S, and 0 otherwise. And now we're just going to consider the quadratic form evaluate from this vector. And so this is a summing over of all pair of vertices, aij times xi times xj. And clearly this is only non-zero if both vertices are in the set S. And so in which case we pick out 1 over S. And because we are promised that S is a clique, each entry of aij is 1. So you have like S squared over S many entries over S here. So it's S minus 1. I mean, it's S choose. It's S choose 2, that's why it's minus 1. You think of it as S. So by special theorem, we know that the special norm is at least the largest clique in the graph. And here's also what we know using results from random matrix theory. With high probability for graph coming from Gn 1/2, it has special norm in most 2 root n. And therefore, we actually have an algorithm that just computes the adjacency matrix of a given graph. And this is already a distinguisher for if you're putting a clique bigger than 2 root n. Because like if the clique is bigger than 2 root n, you can see that from the spectrum. It's going to be significantly, it's going to be bigger than 2 root n. But Okay, now that we have described the algorithm for predicate bigger than 0 n, the natural question to ask is what happens in the in-between regime? Because we know that the typical independent set is at most 2 log n. Sorry, a typical trick is at most 2 log n. But the algorithm only works for 0 n, and there is a gigantic gap here. And one question to ask is whether we can try to close this gap algorithmically in polynomial time. And here's one example of information versus computation. And here's what I mean by the average case setting. That is an average case problem. We are not assuming the input to be worst case. And of course, like predicate is not the only question. You can also ask this for independent set in sparse graph. And there is also an analogous gap phenomenon of like 2n log t over d versus n over root t.
This spectral method algorithm is only the sense performs slightly better than the much more naive algorithm, right? Shaving some log factor.
Yes, indeed. I think for these problems we are looking at, indeed, like brute force is almost impossible.
So are there examples in this domain where spectral methods behave much better than naive methods?
I think matrix completion as an example.
For CS purification, like such methods, it's not clear what brute force on naive algorithm. But for these graph problems, from what I know, like brute force is basically almost. And I think the core message here is also like brute force is optimal for these problems.
True, but then improve low degree hardness be easier than improving SOS hardness, and this in the context of say fixed problems.
Yes, I think you're gonna get. We're gonna talk more about that in a bit. I actually want to advertise why we look at SOS then low degree in a bit. And yeah, and similar examples apply for like reputation for random CSP and also community detection and graph coloring. And for many of these problems, it's always special technique that gives the best algorithm. And here's one thing away from the first part of the talk. Special technique seems to be quite powerful and in fact optimal for these like edge case problems. And the analysis of them usually rely on random matrix theory. For example, in the analysis for predicate research, the only thing we need to use is just a typical matrix has not at most 2 log n. And here's the paradigm I understand for this average case problems is that if you use some special non-bound from random matrix theory, and then you can use it to analyze average case algorithm, and that's usually sufficient already. And a takeaway too is that there is a universal phenomenon of information versus computation gap that's happening in average case problems, and they even find connection to statistical physics. Now let me tell about what, and let me try to convince you why cryptographers still care about like sum of squares, because it would provide you a length of average case capacity. Because cryptographers care about average case hardness, and however, the theory of NP hardness, which use like problem-centric reductions, they do not apply in the average case setting because it's usually hard to preserve distribution using gadget reduction. There's a lot of active research in average case reduction, but based on what I know, they struggle to find reductions between the random 3 set and random 4 set. So there's a lot wide open in these reductions work. Therefore, we propose to study average case complexity using a slightly different angle, which we call instead of applying problem-centric reductions, we want to consider like unconditional lower bound for restricted models. and one model is sum of squares that we are going to see. So for cryptographers, we can think of sum of squares as providing us a powerful test run for studying average case complexity, and this is an algorithmic century perspective. So to study the hardness of a problem, you just need to say, pick an algorithm you like and show that it fails. We will take this as evidence of hardness. And of course, sum of squares is not the only model you might consider as information. You can look at low degree algorithms. Of course, you can also look at statistical query algorithms or local algorithms. But why we want to insist on SOS is really like it's fairly powerful. It captures no strong algorithms and it's universal, applies to a large class of problems, and it's fairly approachable, at least more realistic than trying to prove P versus NP. That said, another reason we want to really stick with SOS is that it also gives us surprising power in terms of algorithmic success. There have been multiple candidates for structured PRGs before Jen Lin's high IO construction. However, they get broken by SOS. So if you want to convince yourself that this is a good cryptographic assumption to start with, it might be good to know whether your particular candidate fools SOS from the beginning.
In this case, if you pose the candidate to cryptanalyst, so what SOS means, you will break it without knowing that. Again, so again, SOS is for proving stuff, and you have some heuristic version that sort of corresponds to it. This has been my experience in this domain.
Yeah, it's the other way.
Yeah. So the question is it true now, like do you know any I'm not sure about I know that the most of to use semidefinite programming get some tools to do some kind of thing. It's not rigorous. It's making heuristic examples.
Would do the job.
Possibly, yeah. So like again, it's interesting to understand and find examples. I'm curious to learn more about your example. I think that even in the context of these more recent results, like and others were involved in local PRGs and getting these SOS attacks and so on. Things like cycle, yeah. So there are simple heuristics that even give you more signal than negative methods.
I think it's coming back to the paradigm of low degree polynomial, by computing.
Like several like degree two PRG I'm not aware of any like low degree. Doing all this just by arithmetic and like it just inverts the input completely. I'm not sure if it qualifies in like SOS framework. Maybe we should talk about it, but it's like slightly different from SOS. But it just inverts things.
That's a great question because in the context of symmetric cryptography, the cryptanalysts work like statistical physicists with intuition, with heuristics, with experiments.
Yeah.
And and again, we don't quite have their training.
Yeah.
I obviously don't have our training, so it's kind of interesting to.
Is there anything from our side which like is new?
Everything on our side is new, but it's relevant.
Yeah.
About you can use SOS to produce hardness for statistical inference questions and take this as a source for doing. So now let me tell about what we know about sum of squares hardness and more generally like how we study higher degree sum of squares problems. As we saw earlier, average case algorithm crucially rely on special numbers following the matrices, and That's the example of kinetic. We're going to say not only do they give you average case algorithm, they also give you average case file. And here's a high-level reason why. The law one you're trying to prove should ideally not break the known algorithms. And because the known algorithms come from special reasoning, your law one should also be relying on some special as well. And more formally, trying to prove this, by definition, you can say sum of squares is at least as powerful as special algorithm because it captures it. But on the other hand, for higher degree sum of squares, for these average case problems, you can think of sum of squares as a gigantic matrix of size n to the order d by n to the order d for degree d, and each entry is just a degree d log n polynomial of the input. So one example of such input is click indicator for a set S in the given graph. So here's a polynomial of the underlying graph. Let me tell you about the typical way of proving sum of squares problem these days. It usually relies on construction of a dual object explicitly, which we call the mole matrix. It's the n to the order d by n to the order d matrix I just mentioned. Or you can also think of it as an operator from that takes like let's see that gives you order d moment, degree d moments in X. And the bulk of the analysis is usually showing the candidate construction satisfies some problem-specific constraint, and that this is a PSD mole matrix. Like this is a valid operator for sum of squares. And this is where like SOS differs from LP and linear programming, and this is also what's giving us a lot of headache in the analysis. And as we mentioned, like morally speaking, you can think of degree d sum of squares as for average case setting as a matrix of polynomial function entry. High degree sum of squares in this case, they usually come down to a systematic understanding of all such matrices, and these are the matrices with entry being polynomial function of the input. And when we look at these matrices, the quantity that's most interesting to us is usually their spectrums or spectral norm per se. And this is also the main focus of like several works in the recent developments. But now let me quickly tell you about these matrices that we look at in the sum of squares problems, but I'm not going to get too much into this. Don't worry. Don't worry about it more. And here's a general setup we consider. We're going to assume that there is an underlying input graph. And for example, it's usually just taken to be the random graph that you care about. And we're going to build a matrix M such that each entry is a polynomial of the input in G, the random graph. And a baby example is just adjacency matrix. Each entry is a polynomial of the input. Of course, this is kind of a trivial example. Like we have very good understanding of adjacency matrix. Now, I want to take a look at this diagram on the top right, and I want to convince you that this actually corresponds to a matrix. And it corresponds to a matrix of dimension roughly n squared by n squared, with rows and columns indexed by 2 tuples in n. In particular, if you look at the AB entry in the row and ABCD entry, essentially, this is going to be a degree 4 polynomial given by summing over the middle vertex, like label the middle vertex, and then once given the label for the middle vertex, you will get a degree 4 point. So the top right diagram actually corresponds to a matrix in sum of squares literature. And we also point out that in general, these matrix entries are not independent. Like, look look at the matrix entries of this MZ, I claim that they clearly do not have independent entries. Because this is a matrix of dimension n squared by n squared, and we only have n squared bits of random in from the random graph sample. So clearly there is inevitably there are correlations across the edges. And these correlations of the matrix entries are preventing us from applying most results in random matrix theory. Yeah, that's all we know about. That's all we need to know about matrix for today. I'm going to shift here back. Earlier, we mentioned that, okay, for degree D sum of squares, you can think of each entry being a polynomial of the input. But I guess I haven't told you what polynomial we are considering. It turns out that each entry's polynomial is defined by pseudo calibration, and which is close, and which, okay, let me tell you about. This is a framework pioneered in the work for Pentacritic. It's inspired by the distinguishing question of UN1 versus UN1 plus KK. The main idea is that the low degree moments of UN1 plus KK is going to help us defining this dual object of pseudo expectation. And here's where the connection to low degree polynomials come in. In fact, if we just focus on e to the one entry of the Moore matrix, so this is just a scalar random variable. It's just one entry of the matrix. We don't even care about the rest. Pseudo calibration is going to set it to the low degree likelihood ratio, which is the focus of low degree polynomial family. And usually verifying e to the one being 1 plus it or 1, but verifying whether your Moore matrix is roughly normalized is equivalent to verifying low degree values for degree D point, actually degree D log A. And now let me quickly sketch about the low degree polynomial framework that I have been arguing with. It builds on the low degree test of a function f. We are going to consider f some multivariate polynomial of the input, for example, graph, and then let's say f has degree m of t. And there are a pair of distributions P and Q that we are interested in. Without lots of generality, we are going to assume that f has mean 0 and variance 1 in a distribution P, just by centering. We call f distinguish these two distributions if the variance of Q, the standard deviation of f in Q is at most the expectation. Like it doesn't fluctuate too much compared to its in Q. And low degree framework gives a way to rule out such polynomials Q f when P and Q are close to each other. And that's it. But what's nice is that I think such calculations are indeed fairly easy to verify these days. Like there is a mature framework of verifying. So let's compare this to sum of squares hardness. Because e to the 1 is just one single entry of the Moore matrix, you can think of it as this question as like just looking at one single scalar instead of looking at matrix spectrum or PSD per se. That said, people do usually view low degree polynomial hardness as a precursor for sum of squares hardness. But this is usually not sufficient. Like there are a lot of examples where we know low degree polynomial hardness, but to get SOS hardness from there, we usually require quite intense case-by-case analysis. And an important conjecture in the area is that low degree polynomial hardness implies sum of squares hardness in general conditions. But I think we are fairly far from setting this conjecture because every example we know right now requires case by case. And here's what we know so far in some of Square's low bounds. Roughly speaking, from 2015 to 2020, we have a very good understanding of problems in the dense regime. This is corresponding to random graph with average degree theta n, or like Gaussian input. Just to name a few problems there. However, when we move to sparse random graph, or just slightly sparser, where for random graph of average degree at most n to the 1 minus epsilon, previous techniques already all fail for this somewhat sparse regime. And in various contexts, we have been trying to ask for sharper and a fine-grained understanding of some of specific regimes. And there have been a couple of work of giving hardness in independent set for sparse random graph, and even and density scale subgraph matching the log density special. And more recently, we have results that gives low bounds in like constant average degree regime, and it has also found generalization to sparse and regular graph, so not just ID. But that said, going back to Yuval's question earlier about logical polynomial, here's a counterintuitive message that I kind of want to get away. It's like, even though low-degree polynomial is easy, it's not always the case that they come before SOS. It's easy to verify, but it's not like okay, let me say, there are examples that we have SOS hardness, but we don't have low degree polynomial.
That means low degree hardness is better to shoot for, like for us, right?
So I think there
Or are you saying that sometimes you might have guesses?
not quite, because I think there are usually some technicality improving low degree polynomial. It's like you need to find a pair of distributions. That's quite. But for sum of squares, usually you care about more, for example, you care about reputation question instead of distinguishing question.
There's some framework that captures both SOS and the Just having two incomparable things.
Yeah. I think for distinguishing question, low degree is still captured by sum of squares. But I'm just using this as like, if you are only looking at reputation question instead of distinguishing, there are cases where you always have trouble finding a pair of distribution that is hard to distinguish. Because, for example, one question is independent set in sparse random graph. We don't have any hard distribution matching n over root d versus matching the n over root d special. But we surprisingly have some more square law saying that the reputation question is hard. And there are more heuristic explanations here. It's like, because you care about reputation question as opposed to distinguishing question in the vanilla SOS formulation, you actually have more freedom in designing the SOS moment. Like you don't have to take the SOS moment as given by the degree polynomial, like similar calibration.
So let's say I come up with an assumption and it feels like a statistical inference problem. I should try to prove low degree lower bounds. Or should I try to show SOS lower bounds as an evidence for getting evidence for hardness? Should I, like, which one would you prefer?
Okay, first of all, I think
like distinguishing assumption.
Distinguishing
Yeah.
assumption. Okay, I think in distinguishing assumption, low degree is still captured by SOS. So you can go for SOS directly if you really believe this.
But you mentioned that there are examples where we don't know how to prove low degree lower bound, but we know how to prove SOS lower bound.
Yeah, so these are the examples where you have trouble finding plenty distribution. Like for example, plenty click is really just a surprise. It's quite a surprise, I would say. Now there's a native, there's a vanilla plenty distribution. It's just you add a click of size k into the random graph. However, you might think of there might be smarter construction of putting the size k click in the graph depending on the local statistics of the graph sample you already have. And yeah, these are the problems where we actually don't know how to paint it, size k key or k bigger than root n in things like in simple things. And another more technical perspective is like low degree polynomial requires e to the one, like the scalar random variable to be concentrated around one. But for sum of squares, ultimately you just care about the matrix being PSD. So it's possible large deviation, but still possible. One personal takeaway I would say, like even though it's more complicated in most cases, sum of squares, there are cases where sum of squares are maybe more probable than low degree. But some questions that I think might be interesting to take a stab at for the future. So one question is, of course, whether we can get a public key from SOS. Hardness, like this has been considered in the context of public key. But what about other hardness? Because the issue with public key is like it only gives you positive polynomial hardness. And one question I'm interested in is like, can we use the sub-existential time hardness in sparse graph? For example, in DKS, that we have known result already to build public key crypto or other cryptographic primitives. And another direction to look at is to consider sharper sum of squares problems in a sparse region. For example, if you look at sparse random graph and average degree is a bounded constant, we believe that we can even achieve exponential hardness here. But current analysis do fall short here. And this is a major open question in this area. And another motivation might be to look at like hard constraints in the sum of squares framework. I believe that these are inherent coming from crypto applications, but sum of squares problems these days do have a hard time handling these hard constraints. So I think that might be another direction worth looking at for future. And okay, here's another area that I think would be cool. So as we mentioned in the beginning, polynomials are expressive and versatile. In that case, why do we still look at reduction for cryptographic analysis? And in particular, I want to ask whether we can design some of squares hardness tailored towards crypto applications. And here's one example in the secret leakage model. I'm going to consider the pentatrick question again, while we additionally review L vertices that are promised to be in the pentatrick. I want to investigate. One question is to ask is like, how does the threshold K change as a function of L? And for here, I'm going to consider L as some constant times log n for some tiny constant, let's say 0.001. And existing sum of squares hardness does not give any meaningful bound for this region of L, even in the dense setting of G1R. But I believe the right bound should be up to point log square root n over 2L. So I think it might be an interesting open question to see if we can get sum of squares from here. And yeah, I think low degree polynomial hardness. The question is whether we can do this in that. And more generally, can we use crypto to identify the next problem to study for some of the problems as we are starting to run out of questions in this area? That's that. I hope I convinced you that sum of squares is an interesting framework to consider, and there seems to be still a lot to do in SOS plus crypto. Thank you.
Sound like fighting all the